So in these next few videos, we're going to take a look at the chemistry of the nucleus. And in order to do that, we need to understand nuclear radiation a little bit, what it is, where it comes from, what causes it, and so forth. So that's what we're going to cover in this video. So let's start off with what is nuclear radiation? So really, well, if you think about the word radiation, radiate means to give off. So in this case, nuclear radiation is the nucleus giving off something, and that something is given off as a result of unstable nuclei breaking down and trying to become more stable. So that's the whole idea. Nuclear radiation is a result of an unstable nuclei breaking down, releasing a particle, energy, both, in order to try and become more stable. So all nuclear radiation is what we consider ionizing radiation. Think about what's in that word, ionizing. Ionizing radiation creates ions. It causes ion formation because it has a lot of energy. It can cause molecules to break apart, like DNA, can cause mutations, can cause electrons to leave the electron cloud, which is how you get an ion. All sorts of damage can happen with nuclear radiation because there's enough energy to cause changes in molecular structures. But radiation is natural. It can be man-made, and we'll talk about that at some point, but we're going to focus on the natural radiation. Almost every isotope has at least one radioactive isotope. That means that nucleus is unstable and at some point in time will undergo a decay and it will radiate some sort of particle out of the nucleus. Because every isotope has at least one radioactive nucleus, we are exposed to radiation every day. We're going to do a lab that you'll be able to see a little bit of that radiation and get an appreciation for the fact that not all radiation is bad. If you're exposed to a little bit of radiation, you're not going to die. That's one of the important things that I want you to get out of this conversation. Like I said, not all radiation is dangerous. It depends on what strength the radiation has, it depends on what type of radiation it is, and it depends on how long you've been exposed, how much, how long, what type, and so forth. So just a little bit of history. I am going to rush through this. If you are interested in the history, I do love the history, but we just kind of don't have time to go through it. So I keep these in here. If you want to look at the PowerPoint individually, feel free. But it all starts right around the turn of the 20th century. First guy to notice radiation is credited for discovering what we call X-rays. X-rays are a form of ionizing radiation, although they are really not a form of nuclear radiation. But anyway, what he did is, using a cathode ray tube, he noticed that he could take a picture of his hand with the cathode ray tube, with the X-rays, the unknown rays that were going through his hand and lighting up a photographic screen behind him. So you can see that the light part is where the rays are going through easily. The dark part is where the rays didn't really pass through. And so he determined that these things were called X-rays and could pass through paper easily, but could not pass through lead and bone very easily. We have Henry Becquerel doing similar research right around the same time. He's credited for discovering the idea of radioactivity. And so what he did, very similar to the last scientist, used something radioactive, in this case uranium. He thought that uranium got its power to glow and give off particles from the sun. And so what he did is, on a cloudy day, He actually put all of his stuff in a drawer, thinking that the sun will not get to it, so nothing will happen. However, he pulled it out the next day, and this is what his paper looked like. His photographic paper looked like this. And so the material actually, the uranium actually gave off the rays, the radiation, without the use of the sun. So then he realized that radiation is internal. It's coming from the inside of the atom. And so here's a good definition to have. Radioactivity is defined as the spontaneous emission of radiation by a material. We've got a few other people to credit with our knowledge of radioactivity. I can't go without mentioning Marie Curie. She's one of the few women who we hear about in this field. They are credited, she and her husband are credited for discovering quite a few radioactive elements, thorium, polonium, and radium, among others. And they hypothesized that some unknown radiation is present in the nucleus and can be absorbed by the element and then re-emitted as energy, which is called radioactivity. Not quite right, but that's what they were hypothesizing. They were the first to kind of start measuring things and establishing standards and so forth. And then we get to Ernest Rutherford. You remember him, right? Discovered the nucleus using the cathode ray tube to bombard gold foil with, alpha particles. Anyway, sorry, my bad. He's actually credited for naming the different types of radiation that scientists were starting to discover. He called them alpha, beta, and gamma, the first three letters in the Greek alphabet. An alpha particle is composed of two protons and 2 neutrons. So 2 positively charged particles and 2 neutral particles. If you look at the periodic table, you will notice that helium actually has this same setup. Mass of 4, atomic number of 2. So an alpha particle is really a helium nucleus because there are no electrons associated with an alpha particle, just protons and neutrons. A beta particle is a high energy electron. Not an electron like you would find in the electron cloud, much, much more energy than an electron in the electron cloud. And then the third particle is not really a particle at all. It's a wave of energy. He called those gamma rays. We're going to get into looking at these three in detail as we progress through this PowerPoint. So what we're going to look at for the rest of the unit is something called spontaneous radioactive decay, because that's what radioactive isotopes undergo. If an element has a nucleus that is unstable, in order to get stable, it's going to undergo a spontaneous radioactive decay. And so here's the idea. Unstable nuclei that occur naturally will automatically, spontaneously undergo a change in the nucleus and become more stable. So what that means is the nucleus is going to radiate. It's going to kick out some particle and become a new element, usually a new element. I probably shouldn't go there completely. Become a new nucleus as a result of the loss of something from that nucleus. The kinds of decays that we are going to take a look at are called alpha, beta, gamma, the three that I just mentioned, but the nucleus could also kick out a proton, so we call that a proton decay, or a neutron, we call that a neutron decay, and a positron, we'll talk about what that is as we move through the PowerPoint. So again, the reason for an unstable nucleus, or the reason for an unstable nucleus, is going to help us predict what kind of decay it undergoes. There are three primary reasons for nuclear instability, and we're going to get to all those. But before that, I'm going to do a side note. So this is not a slide that you have, so you're going to have to kind of listen to my words and kind of take notes. The particles that are ejected, the alpha or the beta or the gamma, those are very short-lived. Although the particle can do damage to you, they don't stick around for long, and it's a very short location that you have to worry about. Gamma rays, alpha particles, and so forth, they don't travel across long distances to hurt you. If we're worried about radiation, what we're really worried about is these unstable nuclei before they decay. So for example, if there were to be an explosion of a nuclear bomb or a nuclear reactor leaked or something, the radioactive atoms would be released into the environment. Those radioactive atoms are super dangerous because they're unstable and Mother Nature can carry them all over the world. Depending upon how far they travel and when they release their radioactive particles, that's when they become dangerous. So if there's a lot of radioactive nuclei in a small area, it can be very dangerous. It's not the particles themselves. Like I said, the particles themselves, the radiation dissipates very quickly. But the radioactive particles can stay around, the radioactive nuclei can stay around for a long time. So it's the nuclei that are really dangerous because the nuclei, the physical atoms, can move all around the world. And when they decay, if you're nearby, then you get exposed to the material. So there's a difference between a radioactive atom and radiation. These guys, the alpha, the beta, the proton, this is the radiation. The radioactive particles are the atoms. So hopefully that kind of clears things up a little bit. What we really need to worry about is radioactive atoms being distributed in large quantities to some location. Okay, so let's get back to these different reasons. So the first reason that a nucleus could be unstable is because it's just too big. So in the nucleus, there are two forces, something called a strong force that holds the nucleons. Nucleon is a generic word we give to protons and neutrons. The strong force holds those nucleons together. So the strong force is an attractive force, but it's very, very short-lived, or not short-lived, it's only good over a very, very short distance. So the particles have to be very close together in order to have the strong force work on them. As the nucleus gets bigger, the particles, protons and neutrons, the nucleons, get further apart from each other. The stuff on the left side of the nucleus is not close to the stuff on the right side of the nucleus, and so there's no strong force necessarily holding those exterior particles together. So that's one force. The other force is what we call an electrostatic force. An electrostatic force is really a force of charges. So you can have attraction between a positive and negative, or you can have repulsion between two like charges. So in the case of the nucleus, there is a repulsive electrostatic force because protons are positively charged. So in the nucleus, you want to have enough protons to keep the positive electrons separated from each other, but you don't want to have too many nucleons so that the strong force is weakened. So big atoms have a lot of protons, so increased repulsion, and diminished strong force because there's so many nucleons. So as the nucleus gets bigger, like I said, the strong force diminishes, the electrostatic repulsion takes over, and pretty soon you have a nucleus that's unstable. When you have that situation, you are going to have an alpha particle emitted when the nucleus undergoes decay to try and become stable. So let's talk about the alpha particle, since an alpha particle decay is what you get. Remember that the alpha particle is essentially a helium nucleus, 2 protons, 2 neutrons. And so the isotopic notation would be something like that. So notice that we have 4,2He, mass of 4, atomic number of 2, because there's 2 protons. But that first symbol is the Greek letter alpha. It is, if you were to draw it by hand, make it look like a little fish kind of swimming. So you can't see me draw it, but ask in class if you're not sure what I mean by that. I'll show you what an alpha particle looks like when we draw them by hand. So alpha particles are very large, mass of 4. That's huge in terms of particles. They're heavy and they're slow moving as a result. So what that means is we can shield ourselves pretty easily from an alpha particle. If you wear a pair of gloves, if you put a pair of goggles on, you're pretty much protecting yourself from an alpha particle. So we also talk about penetrating power. Since the particle is so big and so slow, its penetrating ability is very poor. It can't penetrate the gloves you have on. It can't penetrate the goggles you have on. But if you were to get that alpha particle inside your body, that's very dangerous because now it can't get out. So the alpha particle kind of bounces around inside the cell, inside your bloodstream, inside your stomach, however you got it into your body, whether you ingested it or you injected it, got it injected into you somehow. In order to die from alpha particles, it needs to be intentional. Alpha particles aren't going to kill you by accident. You have to willingly take in alpha particles or unknowingly take in alpha particles from someone in order to feel ill effects from alpha particles. They're not going to get into you by accident. So it's easy to protect ourselves from it. And because they're so slow moving and they're so large, they don't even travel very far. So if you were standing at in the front of the room and I had an alpha source back at the lab area, the alpha particles wouldn't even get to you. They travel only very short distances. But to show an alpha particle decay, we're going to write what is referred to as a decay equation. So if I were to have something like radium, if you look on the periodic table, it's element 88, mass of 226. So in this case, radium-226 is radioactive. Actually, I think every radium is radioactive. But this guy, low on the periodic table, so it's big, heavy nucleus, gonna decay into an alpha particle. So what happens is it splits. It kicks out an alpha particle. This is oftentimes referred to as an ejected particle or a radiated particle. Kicks out an alpha particle. Now, if you write He here, that's great. If you do the alpha, the little fish swimming, notice what I'm doing with my arrow. That's an alpha particle. And so what's left? What I want to do when I write a decay reaction is I want to make sure the numbers on the left add up to the numbers on the right. So 226 loses a mass of 4. What am I left with? 222. 88 protons loses 2 protons. What am I left with? 86 protons. So if you look on the periodic table, element 86 is now Rn, radon. So this is an example of a decay reaction. Happens spontaneously. Nothing is forcing this atom to break down. It just happens spontaneously because the nucleus is so heavy that it wants to kick out some of those particles to try and get smaller. So the strong force is boosted up a little bit. So here's an example that I want you to do. Take a moment. Can you figure out what the product is after this alpha decay? So uranium-238 undergoes an alpha decay. What's the product? Take a moment and figure it out. Obviously, you need a periodic table to do that. Pause if you need to get a periodic table. Hopefully, you figured out that uranium-238 undergoes an alpha decay to produce thorium-234. So again, 238 minus 4 is 234. 92 minus 2 is 90. This is what's left over after an alpha particle gets ejected. All right, so that is almost 20 minutes. I'm going to pause here stop this video and encourage you to take a little bit of a break and then come back to the next video, and we'll talk about other ways that an atom can try to get a stable nucleus.